Good evening, everybody. Thank you for joining me, especially if you're in my time zone, midnight here, a bit more of a USA-friendly time. Now, I'm in London caring for someone at the moment, so I might get called away for a few minutes at a time, but hopefully not. Hopefully they're fast asleep. Right, I'll get straight down to the photos. Full moon is 48 minutes past midnight, so in about 48 minutes time. Right, let's get going. Now, I serve on the altar in Wells Cathedral, and I was the subdeacon on um, the Last Supper feast on Maundy Thursday during Holy Week. And I was given this beforehand, and it had this interesting picture on it. It's actually a picture of the Last Supper by Albrecht Dürer. And the thing that, of course, immediately grabbed me was this, well, what looks like a crescent moon directly above the head of Christ. Now, I didn't realize at the time, but I eventually became aware that it's supposed to be an image of a sort of porthole type window. But as you can see, it's a very odd perspective that it has on it, because we're looking almost horizontally at it, but the way that the perspective is working is as if we're very close to it, looking up very steeply at it. So I just saw it as being a crescent moon. I think, what's a crescent moon doing above the head of Christ? Now, I sent it to a friend of mine who did her MA about Albrecht Dürer, and I'll mention, well, I'll sort of show what she came up with shortly. Now, before that, I just want to remind a little bit about what I did 2 weeks ago, what I showed in relation to the eclipse, this angle of the moon, known as the moon's inclination. So when the moon is on its orbital plane around Earth, twice a month, it'll cross the ecliptic, which is that orbital plane between Earth and the Sun. And if it does that at a time where it passes between Earth and Sun, or behind the Earth with the Sun in a straight line, then you'll have an eclipse. And it happens sometimes, but not always. Now, you may remember what I showed is how this appears to be used in relation to John Michel's diagram of the Earth and the Moon in various cathedrals. And really the best example is York Minster, where the chapter house actually has a skew in its orientation of just over 5 degrees. And it is the moon within John Michel's diagram, as you can see. Now, when I gave this to my friend Lisa DeLong, she's one of my, she's a colleague and a friend from the Prince's Foundation School of Traditional Arts, or the King's School, as we now are. She pointed out this very interesting angle that's going off. Now you can see, or for a start, there's a circle like so, and if you look on the image here, you can see the circle very clearly going around Christ, and all of this, I suppose, light emanating out, all these radial lines. Now, the center of that circle is around Christ's brow. But then you've got this funny angle going off here, which Lisa noticed, and it's in the roof. So if you look off here, going from Christ's brow, going through that crescent moon area along here. That's a very odd, sort of slightly out of kilter cross-ribbed vault. And sure enough, it's just over 5 degrees. So there you go with Albrecht Dürer as well. And I suspect that this may have something to do with the lunar appearance of that porthole. Now, there's quite a lot Lisa found in this, which can be looked at another time. I just wanted to show that lunar angle. Now, if we think about the moon in relation to this particular part of the Christian storyline, then it fits with this idea of the moon, I suppose, disappearing or going through its death and rebirth over the course of 3 days and 3 nights. The sun and the morning star are both very much associated with Christ and with that death and resurrection symbolism of Christ. But the moon, I would say, is there as well because of this 3-day and 3-night association with Christ's death and resurrection, which of course is also associated with Noah, or Jonah rather, in the whale, and also Inanna, the ancient Sumerian Venus, who goes down into the underworld and is dead for 3 days and 3 nights. It's one of these archetypal myths that comes through into Christianity. Now, I just wanted to point that one out, but I'm actually going to move on to something slightly different now. And I'm going to look at a bit of golden ratio Fibonacci numbers and a particular triangle called the lunation triangle, which, as the name suggests, is to do with the moon. Now, you may have come across it before. It's discovered, I think, by Robin Heath. He's the one who's talked about it the most. I'm pretty sure he's the one who was the first one to point out its qualities. Right, so now first of all, I'm going to begin by looking at isosceles triangles that contain phi, which means the golden ratio, 1.618. Now I'm going to show a sequence of these triangles, beginning well, with a baseline of 1, which is what this triangle has. It has a baseline of 1, and then its two sloping edges are 1.618, which are sometimes represented by the Greek letter phi. Now, one of the significant things about this triangle is that its smaller angle is exactly half the size of its two larger angles. So it's quite a significant triangle. And this is also some of the other qualities it has. It is essentially the point of a pentagram star, this particular triangle, and it's also one sector of a decagon, as showing in that image there on the right. So it's a significant triangle, base of 1, sides of 1.618. Now let's lengthen that base of 1 so it becomes a base of 2. But the sides, the sloping sides, are still 1.618, still phi. Now this is the Golden Pyramid triangle, which I talk about a lot in my book, The Cosmos in Stone. It's very similar indeed to the pyramid triangle, which is in John Michel's diagram of the Earth and the Moon. It's virtually identical, in fact. If you scaled this type of triangle and that 11:7 triangle up to the size of the Great Pyramid, there'd only be a few inches different in height. So they're virtually identical, and they're used as if they're one and the same triangle in the design of Wells Cathedral. Now let's lengthen that baseline again so that we now have a baseline of 3. Now again, baseline of 3, but those sloping sides are again 1.618. Now, I don't know if this has got a name. I just sort of found this triangle through experimentation, and so I'm calling it the Golden Pediment triangle, perhaps for obvious reasons, golden ratio and the shape of a pediment. And so these are the 3 triangles that I'm wanting to show here. So as you can see, they're gradually lengthening from 1 to 2 to 3. And this pediment triangle has some very interesting qualities to it that I don't think have been pointed out before. I've talked about them again in my book, because I found them being used in the design of the cathedral at Wells. And that's the only reason why I found it. I wouldn't have found it otherwise. Now, one of the interesting qualities it has, which is used in the design of Wells up at the East End, is if you put both the Golden Pyramid triangle and the Golden Pediment triangle together, so they have the same length of baseline, then their relationship of height is a very good approximation of pi. And that's used within the design in the cathedral at Wells in a really interesting way, what they do with that. Now, this is the other one. This is the one that I really am keen to point out because of what we're looking at with these lunar sessions that we're doing. Now, here is a golden pediment triangle. Now, because the baseline is 3, then obviously half of the baseline, which I've highlighted there, is going to be 1.5, half of 3, simple as that. The sloping side, as I mentioned before, is 1.618. Now, the height is this reasonably obscure irrational number, 0.6066. It goes on to many decimal places. So this is the golden pediment triangle. But let's say that I were to rationalize that golden ratio 1.618 into what one could describe as a Fibonacci approximation of the golden ratio. I'm going to change it to this, to 1.625. Now that's what you get if you divide 13 by 8. You get 1.625, and that's one of those Fibonacci approximations of 1.618. Now, if that happens, you can probably imagine that that line, obviously it's got a little bit longer, so that means that it would have to very slightly raise itself in its gradient. I'm just keeping the same triangle here because it's a bit easier in terms of what we're looking at. But that line, which is 1.625, obviously it has to go very slightly higher up, and that also involves this vertical line here getting a little bit longer as well. Now, the fascinating thing is that when this goes to 1.625, which of course is rational, this one also, this 0.6066 also becomes rational, and it turns into this 0.625. Now, we actually have a very significant and renowned triangle with this rationalization, and we can see it like this. If we take 1.5 and we multiply it by 8, we get 12. Now, if we look at 1.625, and if that's multiplied by 8, you get 13, and 0.625, multiply that by 8, and you get 5. So you have this very significant rational triangle, 5, 12, 13. It's the second one of what are known as the Pythagorean triple triangles. That's where a right-angled triangle has all three edges made of rational numbers. And this is essentially the rational counterpart of this Golden Pediment triangle that I was just talking about a little earlier. Right, let's take a look at the lunation triangle, because that also takes place within the 5, 12, 13 triangle. Now, let's just begin with a few numbers, a few cosmological numbers. 29.53 days in a synodic lunar cycle. So that's the period of time from one full moon to the next, or from one new moon to the next, wherever you have your beginning point. 29.53 days later, on average, you'll be back at the same point in the cycle again. Now here, of course, is the annual cycle of Earth, the amount of time it takes for us to orbit the sun, 365 and a quarter days. Now, to get the significant number that's in the lunation triangle, we need to divide the larger number by the smaller number, so the annual cycle by the lunar cycle, and what we get is this number here, 12.369. So that's the amount of these lunar cycles that we're doing these classes in. That's the amount of them that you get in one solar year. Now, the way in which this shows itself in a 5, 12, 13 triangle is like this. I'm going to put this line in. Now, where this line, like where this line is defined, you know, where it's ended up on that vertical edge of 5, it's like this. If you divide the vertical edge of 5 into 3 and 2, that defines where the dotted line is going to. Now, this dotted line, as you can probably see, it's going to be a bit longer than 12, but it's not going to be as long as 13. Now, the actual length of it, very accurately, is 12.369. And so hence you have this association with the moon. And so hence why it's called the lunation triangle. Now, I'm going to talk a bit about Fibonacci numbers before I then go back to the lunation triangle to show another lunar measure, which I found in my research. So another measure to add to that one that Robin Heath has pointed out, the 12.369 Now, I've talked about Fibonacci numbers a lot in previous talks and in various other talks that I have on my YouTube channel, so I won't go into them in detail. I'll just list them from 1. So 1, you have another 1, and so those two ones together make 2, and then 2 plus the 1 before it becomes 3. 3 plus 2 is 5. 5 plus 3 is 8, and 8 plus 5 is 13. Right, so that's where I'll stop. Now, in that lunation, or in the 5, 12, 13 triangles, the Fibonacci numbers that are there are obviously the 5 and the 13. Now, what we saw with that vertical edge of 5 is that it was split up into its two constituent numbers, 2 and 3, which are the Fibonacci numbers that precede 5. So that brings more Fibonacci numbers into that 5, 12, 13 triangle when we do it as the lunation triangle. Now, if you do something similar with that edge of 13, then you get the number 8 that appears to be missing from this lunation 5, 12, 13 triangle. But we can bring that in, and that is what gives this other lunar measure. So if we have 5 and 8 equaling 13, that's what we're going to do with the diagram now. So if we swing the vertical of 5 up onto the edge of 13, we can divide that hypotenuse, that long sloping edge, into 5 and 8. Now, this is what leads us to this other lunar measure. So I've just highlighted that bit on the right where the edge of 8 is. Now, if you put in that vertical, you drop the vertical from that particular place, then the horizontal baseline is 7.384, which is essentially, well, you could call it the synodic week, in the sense that it's exactly 1/4 of 29.53, which So if we multiply this by 4, you end up getting to the 29.53 days in the synodic lunar cycle. So this lunation triangle, it doesn't just have that amazing 12.369, it also has this other measure too, and all happening via Fibonacci numbers, because of course this, to get here, we looked at 2, 3, 5, 8, and 13. Now, there's so much lunar measure around the Wells Chapter House. And this is yet another thing. I put this in the book as well. Um, this is one that I haven't really shown very much before. This is the first time I think I've shown it online. Now, here is that wonderful staircase. I mean, even before you start counting, you're just wowed by the beauty of this wonderful staircase. It really is a masterpiece. Now, here is the ground plan looking at the staircase from overhead. Now, I think I mentioned last time, and I have mentioned on various other talks, that this staircase contains 29.5 steps, so the nearest sort of rounding up to 29.53. You can actually also count 27.33 steps as well. Now, I won't go into detail with that. That's all in the book, but you can count both of those numbers. 27.33 is the sidereal lunar cycle, which is basically the amount of time it takes for the moon to go around Earth once. It's a bit shorter than the synodic period. Now, I showed 2 weeks ago how there's also the inclination angle within that vestibule that leads into the chapter house, which is itself the moon within John Michel's diagram. So you have this very lunar area, but here's yet another lunar part of the staircase, and it involves 12.369. Now we're going to look at the first 16 steps. Now the 29.5 and the 27.33, they're to do with the fact there's this part step at the beginning, but we're going to just look from the first full step. So we've got 4 steps here, the first 4 steps in the staircase, and their measure, what the arrow is showing, their step, as it were, their depth of step, is very accurately 3 of the cubits that are used within the cathedral. So they're all 3/4 of a cubit in their step, as it were. Now, if we take the following 12 steps, as you can see, that sort of goes within this next architectural zone between these 4 pillars here, which go up to its own sort of separate area of ceiling vault, and it's where the staircase begins to go into the curve. So we've got 4 steps here, and then we have another 12 here. So we have 16 steps in all. So we can say 4, 8, 12, 16. So one would assume that you can extrapolate from that and say that the measure is going to be 3, 6, 9, 12. But it's not, because as you go further up the staircase, the steps are slightly different in their measure. And so, yes, you guessed it, it's actually, in altogether, 12.369. So there's another, in this area here, 9.369 cubits to add to that 3. So the whole of this distance is 12.369. When you would, I suppose, expect it to be 12 because of this first set of 4 steps being 3 cubits. So there's yet another lunar measure. Can this all be a coincidence? I personally think not. Now here also is the wonderful medieval clock in the cathedral at Wells. Of those 3 dials that you can see going around, it's 24 hours. You've got midnight at the bottom, midday at the top, so rather like the sun going from the lowest point up to the highest point, as it were. This is the minute dial in the middle, and or in this bit here. Then the very middle is a lunar dial, and this actually shows the phase of the moon as it is at the time that we're looking at the clock. So obviously now that in the cathedral at the moment, it will be completely full, and that gold area will cover the whole of the circular disc. But it shows the correct phase of the moon. Now, just to show you the knowledge of the clockmaker, of course, the clockmaker knew 29.5 days is what you have in a lunar cycle. And that's why when you look at these numbers, you see 26 going from the right, 26, 27, 28, 29. And when you get to 30, it's just this little block squeezed in, because the clockmaker, of course, knew there's 29.5 days, and the clock does actually work, keeps very good time. Its mechanism, its original mechanism, is actually in the Science Museum and still works. So that shows that 29.5 on the clock, but done as if it's 30. Okay, right. Now I shall de-share my screen. Right. I shall say hello. Oh, on camera. Hello. Thank you for joining me at this time. It's really good to see all of you. Right. I will switch back to my drawing camera, and we're going to draw the Golden Pediment triangle and that 5, 12, 13 equivalent. And they're basically as good as the same triangle. When you measure them afterwards, they'll probably just look the same because their difference is probably about a pencil width or even less. But we're going to do one geometrically. The golden ratio one we'll do geometrically, whereas the 5, 12, 13 we'll just do with very simple rational numbers off the ruler using an inch ruler as usual. Right, on with the glasses, and I'll highlight my screen for everyone. Right, so we want to begin with the ruler. We'll just sort of mark out how we're going to draw and where we're going to draw on here. We want to make a mark 6 inches down from the top of the page. So make one mark here, do one in the middle, and do one over here as well. Just measuring 6 inches down, making a little mark, then we'll draw a horizontal line across. And so that's why we need to have one in the middle too, unless you've got a long ruler that can go over the whole page. Now, I'm actually going to turn my paper temporarily. I'm going to turn it this way. So like I say, 6 inches from top down to the middle. And one somewhere around the middle. Now, I will say it'd be good to be quite fussy with accuracy with it because I tried doing this a bit earlier, and you've really got to be accurate to make it work. So if it's not accurate, don't worry too much. So I'm sort of showing you the geometric rationale behind all of this. Um, but yeah, it's even if you're a little bit off, it makes quite a big difference. I mean, obviously, it's really important to remember with geometry that we can only ever do a perfect or an imperfect copy of all of these geometries. And that's a very sort of Platonist thing to say, really, because I mean, the fact we've got a line that we can see means it's not a line, because a line, technically speaking, only has length. It doesn't have any width. So the very fact we can see the line means it's not a perfect line. So it's impossible to draw the perfect pattern. Just do the best you can, and we can give ourselves an image of the perfect through the imperfect. That's really the way of looking at it symbolically. Right, so to continue marking out, I'm going to make a mark from the left side of the page, 1.5 inches along the line. So I'll make a mark there, 1.5 inches away from the left side of the paper. And having done that 1.5 inches, I'm now going to mark off 6 inches. So 1.5 inches, and then from there, 6 inches. So altogether from here to here is 7.5. Now, if we go to the other side of the paper, I'm going to measure 1.5 inches in from this side as well. So 1.5 inches there too, and again, 6 inches beyond that mark that I've made. Now don't worry about this measure. Oh, it does look so it's a what, 1.5. Mhm. So I'll go over that again. This mark is 1.5 inches in. This mark is 1.5 inches in. And then from those two marks, we do 6 inches from there to there and 6 inches from there to there. Right, I'm going to take a heavier pencil. I'm going to take my HB pencil now and make those 6-inch lines stronger. Now, the reason why we've got these 6-inch lines is because we can relate to both of them via the Golden Pediment triangle and the 5, 12, 13 triangle, or rather the two 5, 12, 13 triangles that are going to be sitting together as if they're like a Golden Pediment triangle. Now, the reason for that is because obviously with 6 inches, we can say that we've got a baseline of 3, because you remember the Golden Pediment triangle, baseline of 3, sloping sides of 1.618. So obviously 2 inches here counts as 1 unit. So we've got 1, 2, 3. Now, because it's 6 inches, we can also look upon this as being, if you think about it, the 5, 12, 13, we were looking at half of it. So that, say 5, 12, 13. So if we're doing two 5, 12, 13s, we're doing another one here, that means the baseline would need to be 24 units. And we have 24 quarter inches here. So 1, 2, 3, 1, 2, 3, 4. So there's 4 in each inch. So 4, 8, 12, 16, 20, 24. And half of that would obviously be 12. So that would be the 5, 12, 13. Right, the next thing that we can do is to take 6-inch measure. I suppose we could take 6 inches off the ruler. Hopefully your compasses are wide enough to do this. If not, I have to admit there's not much I can do to help. It should hopefully stretch that much. If you are having problems with that, if you can stretch your pencil out, if you can make your pencil longer, well, then that'd be one way of doing it. Now, obviously, this should be the same as what you have on the line as well. I'm going to actually draw a couple of vesicas. And we'll use these vesicas to produce these two pediment triangles, the rational and the irrational pediment triangles. Right, I'm going to also put in the vertical within each one of those vesicas. Doesn't need to be too strong, just strong enough so you can see it. So I'll firm mine up a bit so you can see it in the camera. Yeah, you can just about see that. I don't want it to be too strong, so that's why I'm not wanting to do the line very heavily. I just want it to be a sort of construction one. That's why I'm going to do this one just a little bit more. Now, there's a very nice way of geometrically dividing a line into three. Of course, if we use the ruler, we could just divide it into 3 in units, 2, 4, 6, inevitably. But I might as well show you this geometric way of dividing a line into 3. It's quite a useful thing to know. Right, as you can see, I'm going into the middle of this vesica where the vertical crosses the horizontal line of 6 inches. And I'm going to actually reduce the size of the compasses. It's basically reducing by half so that I can draw something. I can draw something inside here. There. So we want to have that at the midpoint. And I'm going to draw a semicircle, like so. Now, while I'm about it, I'm going to. So you see the point of the compasses has gone in there, and I'm going to make a mark like so. Same radial measurement that I already have on the compasses. If you're used to geometry, you'll be aware that I'm sort of dividing this up into 1, 2, 3 equal parts. Now, what you then do to divide this line into 3 is to quite simply draw from here. I'm only actually going to draw the amount of this line where it cuts like so. So obviously you could put that whole line in if you wanted to, but just if I were you, I'd just put that cut in there. And that gives us 1/3 of the line. I mean, we can check with our ruler just to see how accurate it's been. But technically, geometrically, that should be a tri-section of the line. And yeah, that'll do. So hopefully you found that that has worked for you as well. Now, if not, if it's slightly off, then you can use a ruler. And I think for what we're going to do here, I'm going to actually get my initial measurement from the ruler anyway, though obviously I could take it from here. Let's see if it is 2. Yep, that'll do me. Right, so we're going to geometrically, as in with compasses and ruler, not with units of measure, we're going to geometrically produce the Golden Pediment triangle here. And then with simple units off the ruler, we'll get the 5, 12, 13, or 2 5, 12, 13s here to create a rational pediment triangle. Now we need to geometrically produce, well, it's sort of producing a square really. We're doing the underlying geometries for producing a square. Perhaps I'll just do that a little bit stronger, because let's see that it doesn't show up so much on the screen. Now, the length of these two arcs is basically so that if we were going to draw vertical lines down like this, we'd want to be able to cut those lines down there. So that's what defines. So you sort of do it by eye so that it drops down to directly below these 2 points. Now, the other one that we can put in using the same 2 points is just a little cross up here. So using those 2 points, same measurement that you have on the compasses, get that little cross up there. Now, the reason why we need this is so that we can get just a little mark on the line. Like so. Now, of course, because we've bisected this, it should be 1 inch. Right, once you've got that little mark there, with the same radial measurement on the compasses, you should find it does that. We want to do this. A simple mark. It's like making the tail of the fish. So that one there, having put that middle point in there, ruler between here and here, that went in, and then with the measurements like that, it's the same as the measurement that we did this with. But what we do is go into that midpoint that we produced and then put on that little mark there. Right, so what I'm going to do next is put my ruler between, cross all the way through like that, and just make a little mark like so. This is a way of producing a square when you only have one edge that you're starting from. Because what I'm going to do now is point my compasses back in here, and I'm going to reduce by half so that I have this measurement on the compasses. And then you can go to here. Into that crossing and make a little mark on one side and a little mark on the other. And in actual fact, I'm gonna, my line on this side wasn't quite long enough, so I'm just a little bit longer. Though we're not actually using this, to be honest, but might as well get it done neatly. And this is where the accuracy, hopefully, is okay. Because what I'm going to do now, point the compasses in here, and then pencil on that crossing point there. Now, if you're wondering what we're doing here, this is the way to produce a golden rectangle. What we've effectively done is got a square here, and then I'm going into the middle of one of the edges of the square and going diagonally across to its corner, and then bringing that measurement down. And so that then, if this is 1, this is 1.618. Fingers crossed it is anyway. So having got that point there, I'm going to bring that across like so. So if we have our baseline of 3, what can be said is that from here to here is 1.618. So I'm going to take that measure onto my compasses. And you can see, because obviously this is going to be 1.5, so it's just a little bit more than that. Now, where that crosses the middle line, we can do the same thing from here. That should be the peak or the apex of the Golden Pediment triangle. Now I'm going to cheat and just use my ruler to see if it's as I want it. Yep, that's good. Good. So you should hopefully find that that cross, the middle of the cross, coincides with the vertical axis. And what you can then do is put in Golden Pediment triangle. So that's the one that is, if this is 1.5, as in if this here is 1.5, the whole thing is obviously 3. That's 1.5, that's 1.618. And then this one is that obscure measure 0.6066. So there's a geometric way of drawing this type of a triangle. Now the simple units way is, you remember I said that it's quarter inches, so 4, 8, 12. So we've got the edge of 12 here, and I'm just going to take 5 of those quarter inches from my ruler. So this is 5, 12, 13. But what would be quite interesting now is if you check, just sort of put your ruler across to those two apexes, and you might be able to, have marks on your ruler down here that you can sort of make sure are sort of running parallel with these lines. And you should find that these two apexes really are virtually identical. If there's one that's going to be ever so slightly higher, it's going to be this one by a tiny amount. I mean, what you can do, this is 1¼ inches here because it's 5 of those quarter-inch units. You can measure this and see what you get with that. Now, this is very accurate. This is good. I'm happy with this. This is ever so slightly, a tiny bit less than 1¼ inches, which it should be. Now, various people have said when I've shown them this, they've sort of said, "Is that um, the type of thing used for the pediments in Greek architecture?" Well, I wonder. Who knows? It'd be very interesting to sort of analyze some and see if any of them do have that particular measure within them. Now, while we're at it, why don't we also put in, I'm going to divide this, so 1, 2, 3/4 inches. Might as well put in that lunation. So that would then be 3 to 2, and that's 12.369, the amount of lunar cycles in the annual cycle. I suppose we might as well put the other one on here, on the other side. Right, so I'm taking the height like so. So now we have 5 here, and 8 here. Aha, now there's a challenge. I haven't ever worked out how to make sure that vertical is vertical. You could just do it by eye. Or another way might be to that's a bit too late for me to think on my feet and work out a proper geometric way of doing this. So I'm just going to do it by eye and taking that measure there. That's very interesting. That looks as if it's very close. I'll have to look at that. I'll have to analyze that, see if there's anything in it. And I'm going to go to here, do this. So I just basically, I did it by eye, really. I didn't do it properly geometrically, but it's good enough, especially when it's close to 1 in the morning. 7.384 and 7.384 times 4 equals 29.53. Right, I'm going to go very briefly back to slides, just to give a few more reminders of things that are happening shortly. Now, I'm very near to getting the proper information for all of these courses that I'm going to be running next year. First one will be in September, late September at Michaelmas, and that'll be glass painting and labyrinth. And then, as you can see with all of the other descriptions there, there'll be these various different courses running through the year. So if you do all of them, then you have that whole seasonal cycle of courses. But obviously, if you're not free to do all of them and you want to come to some of them, that's fine as well. But I'll have more information ready about more detailed information about each one very soon. Now, I'll also mention this one. I mentioned this one at the last session. This course that's going to happen in Wales. We're going to look at the tetractys. This was the form that was the Pythagoreans swore an oath over. 1 + 2 + 3 + 4 equals 10. So myself, Daniel Doherty, and Adam Tetlow we'll do about a day of teaching each. I think we'll probably do half-day sessions, and we'll sort of swap them around as we go. So do come down for that if you want to. And there's also something that I'm calling a tetractys walk, which is right near the end of my book, which is a walk that you can do through the cathedral from west to east, where as you go through diminishing golden sections in terms of the distances that you're walking, you see each new level of this tetractys window that you're looking at here. So in a sense, you're ascending the tetractys by walking these diminishing golden sections. It's fascinating. I mean, again, I can't absolutely prove it's intentional, but it works very well indeed. Right, everybody, it's bedtime, especially if you're on this time zone. Thank you for joining me. I'm really glad you could come. It's full moon around now, in fact, so I hope you managed to get some sleep, because it's not really a very sleepy time at the full moon. The next session, new moon. Now this is, God, I've been waiting for this one for all year. This is 4 o'clock in the morning I'm going to do next time. So feel free to join me if you're feeling very bold. It might actually be light at 4 in the morning at that time, but if you don't join me, feel free to watch it online, but I'll be there. Okay, everyone, I shall say goodbye. Thank you very much. Thanks for coming. And I may see you next time. If I don't worry, I'll understand. But hopefully see you at some point soon. Okay, bye.
Thank you. Thank you, Tom.
Thanks for coming.